Today we are discussing Poisson bracket. It's a very important and elegant construction in classical mechanics. Actually, this is a French guy, and his name has to be pronounced as Poisson. All right, but we usually anglicize it and say it as Poisson. So yeah, that's how it's done. All right. Now, we don't know exactly how he came to this construction, but it's possible that he thought along these lines. All right. Suppose you have some function u of qi comma pi, right, in the phase space. All right, some function of the phase space point or the representative point. All right. So this means that we know that this the representative point in phase space evolves with time according to Hamilton's equations. Okay, and then this means that corresponding to each value, you have got a value for this function, right? So this function also evolves with time. Okay, as the representative point evolves in time, this function also evolves in time. Okay. Now, what's the time evolution of this function? Suppose we need to find du by dt. We also call it as u dot. Okay, du by dt. We know that by this chain rule, this is equal to dou u by dou qi dot. Okay, summation over repeated index is implied here. Okay, all right, plus dou u by dou pi dot. So we imply Einstein summation convention. Okay. All right. Now we know that qi dot, okay, by Hamilton's equation, we know that qi dot is, okay, so this is just an evolution, time evolution of a function of qi and pi. Okay. So yeah, qi dot is dou h by dou pi, we know that, plus, and this is minus dou h by dou qi. Is that correct? Yeah. Okay. Now such quantities keeps appearing everywhere. All right. Dou u by dou qi, dou h by dou pi minus dou u by dou pi, dou h by dou qi. Okay. Now, so when maybe this is how Poisson came to this idea of Poisson brackets. Okay. The idea is that when you look at the evolution of some function of the phase space variables qi and pi, such quantities always appear. Okay, such quantities or such equations always appear. Right. Now, why not use a shorthand notation for this and write this as? Okay, so since this appears everywhere, all right, you take the derivative of the function with respect to space, with respect to generalized coordinates, and then the derivative of the Hamiltonian with respect to generalized momentum, and then invert. Okay, not invert, reverse the order of these derivatives and get a minus sign. Okay, so Poisson said that, okay, let's get a concise notation for this, and let's represent this as u comma h. Okay, the definition of u comma h being defined by this. Okay, dou u by dou qi, which means that you take the derivative with respect to a coordinate of the first function, okay, multiplied by the derivative of the second function with respect to the momentum, generalized momentum, minus in the opposite order. All right, this we call as the Poisson brackets. Okay, Poisson. This is known as the Poisson bracket of u with. Now this is how we define this Poisson bracket. Now we can generalize this. All right, this need not be the Hamiltonian. We could define the Poisson bracket of any two functions of the phase space. All right, we can define the Poisson bracket of any two functions. Okay. So simply let's if u and v are functions of some phase space variables like that, then we can define u comma v. Okay, the Poisson bracket of u comma v by just this prescription. All right, this is dou u by dou qi, okay, dou v by dou pi minus dou u by dou pi, okay, and dou v by dou qi. Okay, just reverse and you get a minus sign. That's correct, isn't it? Now remember that I'm not putting the summation here, so because it gets a bit, but remember that there is a summation over there. All right, summation over I, because I is repeated. So I may not be putting it everywhere. It's difficult to keep track of the summation sign. So let's just follow Einstein's summation convention. Now this is the definition of Poisson bracket. Okay. Now this is a very elegant structure, right? And it simplifies the notation a lot. It also gives a lot of new ideas. For example, we can see that this is a direct way of going into quantum mechanics from classical mechanics. In quantum mechanics, we have a very similar structure known as commutator bracket, which follows almost all the same properties. Okay. All right. So now this is very important. Poisson bracket is very important. We'll see later that this is also this also has some sort of invariance when you go from one set of coordinate and momenta to another set of coordinate and momenta, known as what do you say, the canonical transformations. So we'll be seeing canonical transformations next. So this is very important, and there are problems using it. We can solve them. So we can look into some properties of this. Okay? So just this is the definition, right? This is the definition. You just take the derivative and of all the coordinates, you need a summation over I over there. And using this definition, you can derive some of the important properties of the Poisson bracket. Okay. Also, the conservation laws and there are things can be written in a very nice way, whether it's space translation or rotation or time translation. It can always be written as a Poisson bracket with some function there. All right. For time translation, you know that it will be the Hamiltonian, but we'll see this. Okay. Now let's look at some of the properties. This is very important, very important. Okay. Now let's first look at the fundamental Poisson brackets. Okay, this is very easy. If you take Qi with Pj, okay, Qi with Pj, all right. This means it could be Q1 with P1, Q1 with P2, or something. This will be equal to simply delta Ij, which means that if I is equal to 1, so I is equal to j, this is 1. If I is not equal to j, this is 0. This can be seen from here, right? Okay, Qi with Pj, you can see how it is done. All right, you just look into this definition. This is equal to, now since I am using Qi and j here, for summation index, I'll use k. All right. So this, by definition, I can just check this. This is very important. You have to remember this, and it's easy to remember also. Okay. If it's if it's x with px, it's 1. If it's x with py, it's 0. If it's y with py, it's 1, etc. Okay. Now this is equal to this. You can write it as dou u by, sorry, in place of u, you have a Qi here. In place of u, you have a Qi here. So this becomes, this is, I'll just prove this one. Okay. This is dou Qi by dou Qk. Right. K I have used for summation. Dou Pj by dou Pk. This is summation index. All right. Qi, in place of u, you have Qi. In place of v, you have Pj. Minus dou Qi by dou Pk dou Pj by dou Qk. Is that correct? Okay. Now what is this? This is equal to dou Qi by dou Qk. This is simply delta Ik. All right, delta Ik, which means that if it's the same coordinate, you get a 1. Okay. And this is delta Jk. And this is 0 because Q and P are independent by construction. By definition, they are independent. So this term is 0. Dou Q by dou P are 0. Now what's delta Ik, delta Jk? This is summation over K. This is summation over K. And it will survive only when, there's a summation over K. This will survive only when, so this can be written as delta Ij. All right, because that's a whole summation. We sum over all possible values of k. All right. Okay. And you'll see that this value is equal to delta ij. Okay. All right. So this is a fundamental Poisson bracket relation. Qi with Pj is equal to delta ij. Okay. Now we won't be proving all the properties because it's rather easy, but you have to remember some of them. The second property, this is clear, isn't it? Is it fine?
Yes, sir.
Okay. So the second one, okay, sometimes you also write the index here with respect to q and p, etc. But that's not always needed. But if you have different sets of coordinates and momenta, it's better to write that. Okay. Now another important thing is Poisson bracket of a function with itself, okay, is identically 0. Okay. Poisson bracket of a function with itself is 0. It's easy to prove. I'm not going to do it here, but we can just say this thing, u comma u. All right. U comma u is equal to 0. Okay, that's really easy to see because this is dou u by dou qk, dou u by dou pk minus dou u by dou pk, dou u by dou p. That's the same term. So it's equal to 0. Okay. Now, again, we can see another one. Poisson bracket of a function with a constant, with a number, okay, with a constant or with a number is 0. Okay. So this we can use for solving problems. For example, if you have u comma c, that's equal to 0, where c does not depend on the coordinates. Okay. And then there's this distribution law. We have got the distribution law. This is important. Okay, all these properties are important.
Square bracket ഉപയോഗിക്കാമോ സാറേ Poisson bracket നെ?
അത് സ്ക്വയർ ഉപയോഗിക്കാറുണ്ട് സോറി, ഞാൻ കൺസിസ്റ്റന്റ് ആയിട്ട് ഉപയോഗിച്ചാൽ മതി. സ്ക്വയറും കേളി ബ്രാക്കറ്റ് ഉപയോഗിക്കുന്നുണ്ട്. പക്ഷെ നമ്മൾ ക്വാണ്ടം മെക്കാനിക്സിലേക്ക് വരുമ്പോൾ square bracket in quantum mechanics, square bracket is usually used for the commutator.
Okay, sir.
Okay. But then curly bracket is used for anti-commutator. So you can use square bracket. Okay, we could use square bracket everywhere. Then it's consistent. Okay.
Okay, sir. Okay.
It's okay. So I may make this mistake of doing square bracket instead of curly bracket, but remember that it's all Poisson bracket. We don't have any other bracket right now. Okay. So we'll use either square or curly bracket, depending on, for example, in a problem, they may give the Poisson bracket to a square bracket, then we'll use the square bracket, etc. Okay. All right. Now we have got this distribution law. If you have something like u plus v phi, okay, u plus v with phi, this can be simply u with phi plus v with phi. Okay. All right. And we don't have to prove this, right? It's really easy because this is the property of derivative. When you take the derivative of this derivative of first term plus derivative of second term, so you can just rearrange them to get this term. Okay. And the fifth one, okay, fifth one is u comma v is equal to minus v comma u. Okay, this is known as antisymmetry. It is antisymmetric. Okay. If you interchange, you will get a minus sign, which means that, for example, if you have, we said that qi with pj is equal to delta ij. This means that pi with qj is equal to minus delta ij. Okay, we'll use this. Then we have got this property. Okay, so if you need to take the Poisson bracket of a product of two functions with one function. Okay, for example, u v with phi. Okay, this is a product of two functions u and v. Now this can be written in this way. This is equal to, okay, these relations, all right, all these relations except for this, there will be an IH course in quantum mechanics, but the fundamental relations that we are writing down, these are also the same in quantum mechanics. Okay, the commutator relations. But commutator, you have to be careful. You need to be careful about the order of multiplication. Here, you need not be careful. That's all. Okay. All right. So this is equal to, this can be written as u comma phi multiplied by v, okay, plus u v comma phi. Okay. Here I have been careful about the order uv. Okay, uv is there. So u is the first one, v is the second one. So I have kept the order here. All right. U appears first and v appears second. Here u appears first and v appears second. So that order I have kept. In Poisson bracket, you need not worry about this order. Okay, in quantum mechanics, you have to worry about this order in commutator bracket. So in classical mechanics, we can simply write this as u v phi plus v u phi. Okay, or the other way, it's the same. All right. So in quantum mechanics, we cannot write this. In classical mechanics, we can write this thing. Okay. So that's important. And another property. Okay. All right. We can look into the Poisson double brackets. Property of Poisson double brackets. Okay. So what we mean by double bracket is construction of this form. Suppose you have three functions, u, v, and w. Okay. Then what you call a Poisson double bracket is this. We take u, v with w. Okay. First you take the Poisson bracket of u and v, and then take the Poisson bracket with w. Okay. You also have other double brackets here. For example, u, v, w. Let's take, I'll give another example here. I'll give you three examples. So the other one would be let's write it as v comma w comma u. Okay, that's the reason why I take this particular combination. And you also have 3, 1, 2. W comma u comma v. Okay, w u v. Okay. Now this I have taken sort of a cyclic permutation. Okay, 1, 2, 3, 1, 2, 3. Okay, this is 2, 3, 1, and 3, 1, 2. Okay, I've taken a cyclic permutation. Right? U no 1. U1, V2, W3 in the cyclic permutations 1, 2, 3, 2, 3, 1, 3, 1, 2. Okay. Now in this case, there is this relation. This sum of these three are equal to 0. Right? This is known as the Jacobi identity for Poisson brackets. W plus VW comma U plus, okay, it's not very difficult to prove it. It involves a few steps of algebra, but it's a good thing to remember. This sum is always equal to 0. Okay. Similarly, you can also find this sum. Okay. Also in cyclic permutation, U VW, okay, plus VWU, okay, again 2, 3, 1 plus WUV. Okay, this is also equal to 0. So basically, you take the cyclic permutation of these three functions and construct the Poisson brackets accordingly, add all of them, or add all the double Poisson brackets corresponding to the cyclic permutations of u, v, and w, then this will be equal to 0. This is known as the Jacobi identity. Jacobi identity for Poisson brackets. Okay. Okay. So these are the important properties that we'll be using in problems. Let's look at some of the other features, other importance, the importance of Poisson bracket. Importance goes like this. If you look at, we already saw this one, right? If you look at Hamilton's equations of motion, we have dou h by dou pi, and pi dot is equal to minus dou h by dou qi. Okay, so this, as we said earlier, if we have f dot, we can write as f with h. Okay, in the case of f, you have a q here and you have a p here. So by that relation, this you can simply write it as qi comma h. All right, the Poisson bracket with h. So in this way, you can say that the Hamiltonian is the generator of time translations. Okay, because you need qi dot, you just take a Poisson bracket with the Hamiltonian. Okay, so in this sense, you can say that Hamiltonian is the generator of time translations. All right, you also have pi with h. Okay, this we already saw earlier. We saw it in case of f. Here we have got q and p in place of f. Okay. Wait a second. Yeah, let's start it. You can check this, all right, because qi with h, for example, this is equal to dou qi by dou qj. I'll just check this one, okay, just for it to be sure. Dou qi by dou qj, dou h by dou pj, okay, minus dou qi by dou pj, dou h by dou qj. Now this term is 0 because they are independent. So this becomes delta ij dou h by dou pj. What's dou h by dou pj? That is simply qj dot. So that's equal to delta ij. Sum over all the j, this becomes qi dot. All right. So you see that qi dot equal to qi with h. Similarly, you'll see that pi dot equal to pi with h. Okay. And we can say from this relation, all right, looking at this, we can identify h. Okay, or from this relation, we name Hamiltonian as the generator of time translation. Generator of time translation. Okay. All right.
സാറേ അവിടെ ഡെൽറ്റ ഐ ജെ നമ്മൾ ക്യൂ ജെ ഡോട്ട് എന്ന് എഴുതിയിട്ട് പിന്നെ അതിനെ ക്യൂ ഐ ഡോട്ട് എന്ന് എഴുതാൻ പറ്റുമോ?
അതാണ് ഇത് ഞാൻ പറഞ്ഞല്ലോ, this we imply that there is summation over repeated index. So summation over j. Okay. ഇവിടെ summation over j ഉണ്ട്, നമ്മൾ അത് imply ചെയ്തിട്ടുണ്ട്.
Okay.
So when you sum, this is equal to, ഇത് sum ചെയ്യുമ്പോൾ എന്താണ് കിട്ടുക? Suppose there are just 2 or 3 variables. So that this becomes delta i1 q1 plus delta i2 q2 plus delta i3 q3. It goes like that. Right?
Okay.
But only one term will survive where I equal to j.
Okay.
അതുകൊണ്ടാണ് ഇത് qi ആവുന്നത്.
Okay, sir.
So that's a property, that's a fundamental property of this Kronecker delta. You have to remember this property. We can even define Kronecker delta by this property. If you have something like, let's say, this property is important, right? Xi delta ij is equal to xj. Okay, in this whole summation, only one term will survive, for which I is equal to j. This can be seen as a property of Kronecker delta. Is that clear?
Yes, sir.
It's the same thing we used just before some time, right?
Okay.
Okay, and So now it's very easy to identify constants of motion. Okay. Because the Hamiltonian, we saw that for any function f, we started by this thing, for any function f, okay, df by dt is equal to f with h. We already saw this. This is where we began, right? We showed this actually. Okay. Now, if f is only a function of, wait, let's be a bit more careful. Okay. We started with f being a function of q and p, but generally f can be a function of q, p, and t. Okay. Suppose you have such a function, and then you see that df by dt. Okay. Df by dt is equal to, we already solved it for this thing. It is dou f by dou q, q dot, dou f by dou p, p dot. So that part becomes simply f with h. Okay. But we already saw that in the beginning, right? If f is simply f of q comma p, it is f with h, plus you also have this dou f by dou t. Okay. All right. We said u, but it's f, it doesn't matter. Now, if f does not contain t explicitly, okay, then we can say that df by dt is equal to f with h. Okay. Now this means that f is a constant of motion. F is a constant of motion if, okay, the Poisson bracket with Hamiltonian is equal to 0, and it does not involve time explicitly. All right. F is a constant of motion if, so we can conclude that f is a constant of motion if Poisson bracket with Hamiltonian is 0 and f does not explicitly depend on time. Okay, so this result is important. If you want to identify a constant of motion, you just take the Poisson bracket with the Hamiltonian. Okay. Now this is nice because in order to take the Poisson bracket with the Hamiltonian, you need not do this derivatives. Okay, you can do it using this derivative. Then you are just not using the convenience. Okay, you can just use the fundamental Poisson brackets because f is a function of q and p, right? H is a function of q and p. And you know the fundamental Poisson brackets, qi with pj is equal to delta ij, right? And you know all the properties as to how to combine these two terms. If there's a sum, if there's a product, you know how to combine them. And then simply using this fundamental Poisson brackets, you can check whether the Poisson bracket with a Hamiltonian is 0. You don't have to do the derivatives always. Okay, you don't have to, sometimes you don't even have to remember this derivative form. Sometimes you have to, but most of the cases you can just do it in this manner. Okay. But actually, in all cases, we can do it in that manner, but sometimes it's more convenient to use the derivative thing. Right? Most of the times, it's more convenient to use the fundamental Poisson brackets. Okay. Yeah. And it's another important result is this, right? If let's say Lx, okay, don't worry about what Lx and Ly are. We have got two functions. Okay. If Lx and Ly are constants of motion, then so is Lx with Ly. Okay. This could be u and v. If u and v are constant of motion, then so is the Poisson bracket of u with v. Okay. This can be easily shown using the Jacobi identity. We don't have to prove it, right? We can just give the result here. Okay. So this means okay, if Lx is a constant of motion, then Lx with h is equal to 0. Okay. And if Ly is a constant of motion, Ly with h, sorry, let's use curly brackets. Ly with h is equal to 0. Okay. So then you can show by Jacobi identity that then it can be shown that Lx with Ly, okay, the commutator with h is also equal to 0. All right. The step is really simple. You take three functions, Lx, Ly, and h, and simply construct the Jacobi identity, that relation corresponding to Jacobi identity. You will see that there will be two terms which are 0 because there will be Poisson bracket of Lx with h, that will be 0. There will be Poisson bracket of Ly with h, that will be 0. And then there will be Poisson bracket of Lx, Ly, and h. We are taking all the combinations, right? And that has to be equal to 0. All right. That's how you prove it. Because the Jacobi identity says that the sum of all these three terms is equal to 0. Is this fine? You don't want the proof, do you? You can do it by yourself. Okay? You can do it as an exercise. It's really simple. It's just 2 steps. Okay. Proof. I can put it in the notes if you want. All right. Let's do a problem now. This was asked for NET June 2012. Okay. The question is this: the Poisson bracket modulus R modulus P has the value. Okay. And in the options you have, options are this: modulus R modulus P. Okay. Second option is R cap dot P cap. Okay. Third option was 3 and fourth option was 1. Okay, these are the options. Now we could do this in different ways. Okay. Well, let's just use the definition of the Poisson bracket. So this is simply modulus of R is x square plus y square plus z square. Okay, whole raised to 1/2. Okay, modulus of P is px square plus py square plus pz square whole raised to 1/2. Okay. Now, yeah, this is what we need to find. Okay. So, right. So you have to take with respect to x, y, and z, and px, py, and pz. All right. So the first term, you can imagine this is u and this is v. The first term would be, okay, the first term would be this summation. It would be, let's say this is u and this is v. Then you will have dou u by dou x, dou v by dou px, okay, plus dou u by dou y, dou v by dou py, plus dou u by dou z, dou v by dou pz. All right, this is the Poisson bracket. Am I right? Because I said we have a summation over. We defined it like that, all right, with the summation. Okay. Now there's also the other term, but the other term is 0. Okay. When you do problems, it's really important to identify this. Okay. Because what does the other term consist of? Other term consists of dou u by dou px plus dou u by dou py, etc. Right? And dou u by dou px, dou u by dou py, dou u by dou pz all are 0 because these are functions of x, y, and z. So derivative with respect to px, py, pz are equal to 0. So you don't have to write it out. You just observe that immediately this is equal to 0. Okay, that simplifies it by a huge amount. Okay, is this fine? You don't have to write the second term. That's equal to 0. Okay, there's a minus one. So it's minus. So minus that term is equal to 0. All right. Now you just do this. What's dou u by dou x? It's equal to, you have got whole raised to 1/2. So 1/2. Let's write it as 2 square root of x square plus y square plus z square. Okay. You're taking dou u by dou x, so you'll have a 2x there. Okay. Similarly, here you'll have 2px divided by 2 square root of px square plus py square plus pz square. Is that right? Okay. Plus, similarly, 2y by 2 square root of x square plus y square plus z square. Okay, just taking the derivatives multiplied by, I'm sorry, multiplied. Okay. All right, multiplied by 2py by square root of px square plus py square plus pz square. Okay, and you have one more term plus z 2z divided by square root of x square plus y square plus z square 2pz. Is this clear? Or should I explain more? Do you need more explanation, or is this fine? Okay, I assume this is fine. Okay, all right.
ഒന്നുകൂടെ എക്സ്പ്ലെയിൻ ചെയ്ത് തരുവാണെങ്കിൽ നല്ലതായിരിക്കും.
Not explain ചെയ്യണം അല്ലേ? All right. ഏത് ഭാഗമാണ്?
ഇലാബറേറ്റ് ചെയ്തേ.
ഇതൊക്കെയാണ് ഈ സെക്കൻഡ് ടേം 0 ആണെന്നുള്ള ഓക്കെയാണോ?
അത് മുമ്പേ സാർ പറഞ്ഞ ഇൻഡിപെൻഡന്റ് ആയതുകൊണ്ടല്ലേ?
ഇവിടെ കാരണം ഇവിടെ വരുന്ന ഡോ ബൈ ഡോ പി എക്സ് ഓഫ് ദ ഫസ്റ്റ് ഫംഗ്ഷൻ ഇതായിരുന്നു നമ്മുടെ യു ആൻഡ് വി അല്ലേ? This is what we need to find. Okay, square root of x square plus y square plus z square, comma square root of px square plus py square plus pz square. This is what we need to find, right?
Okay.
So this is the first function u and v. You'll have dou u by dou x, dou v by dou px.
Okay.
These terms are non-zero. But the second term, the minus term, would be dou u by dou px. But this is a function only of x, y, and z. So dou u by dou px, dou u by dou py, dou u by dou pz will be 0. Second term is 0. All right?
Okay.
The first term is this, dou u by dou x, dou v by dou px, plus dou u by dou y, dou v by dou py, plus dou u by dou z, dou v by dou pz. Because we defined it like this, u comma v is equal to dou u by dou qi, dou v by dou pi, minus dou u by dou pi, dou v by dou qi. All right? There's a summation over I, which I did not write, which is implied. Right? So you have to sum over all the coordinates. That's why we have dou u by dou x, dou v by dou px, plus dou u by dou y, dou v by dou py, plus dou u by dou z, dou v by dou pz. Okay, is this fine?
Okay.
Now what's
Okay.
dou u by
Fine,
dou
sir.
x? This is u. What's dou u by dou x? This is a square root, right? So square root of x, you take the
Okay.
derivative is 1 by 2 root x. Right?
Okay.
So it's 1 by
Okay.
2 root square root of x square plus y square plus z square. Now you need to take the derivative of whatever is inside there. You are taking derivative, partial derivative with respect to x, so you'll have a 2x there. Right?
Okay.
Is that fine?
Okay.
Because this is a
Okay,
function of a function, right? You have got a square root and inside you have some other function. So the square root, it's 1 by 2 root of x square plus y square plus z square. Now you need to take the derivative of whatever is inside with respect to x, that's 2x. Okay. Similarly for the other term, it's exactly the same. You'll have 2px by etc. Is that fine now?
Okay, sir.
So what do we have here? This is equal to this can be written as xpx plus, you see the denominator is the same, right? xpx plus ypy plus zpz divided by, okay, you see the square, the denominator is the same. We can simply write this as square root of x square plus y square plus z square multiplied by square root of px square plus py square plus pz square. Okay, just combining all the terms. All right, now what's x px plus y py plus z pz? This is simply, we can write it as r dot p, right? R dot p, because r vector is xi plus yj plus zk, and p is pxi plus pyj plus pzk, right? So r dot p is xpx plus ypy plus zpz. Okay, so this I can write as r dot p, and on the numerator we have modulus of r vector. This was modulus of r vector, and this is modulus of p vector. Okay, so this you can write as r vector by modulus of r vector dot p vector divided by modulus of p vector. And what is this? This is nothing but the unit vector, right? R divided by modulus of r is just the direction, right? This is r cap dot p cap. Is this clear? It's fine, isn't it? Okay. So it is R dot P, and that answer is option B. That option is there in the result. Okay, it's R cap dot P cap. It's fine, isn't it? Okay. So if you have any question, you don't hesitate to ask. Okay, you can always ask. If you don't ask, I assume that you understand all this, and then I'll go. If it's any doubt, all right, whether it's this multiplication or division or even unit vector, anything you can ask. You don't worry about it. Okay.
സാറേ അവിടെ ഒന്നും കൂടെ പറഞ്ഞുതരാമെങ്കിൽ.
ഏതാണ് ഇതാണോ? ഇത് ക്ലിയർ ആണോ?
അവിടെ തൊട്ട്.
ഇത് R dot P ആണെന്നുള്ള ക്ലിയർ അല്ലേ? ഓക്കെ. ഡിവൈഡ് ബൈ മോഡുലസ് R മോഡുലസ് P അല്ലേ? ഓക്കെ. പിന്നെ നമുക്ക് ഇങ്ങനെ എഴുതാലോ, R വെക്ടർ ബൈ മോഡുലസ് R, P വെക്ടർ ബൈ മോഡുലസ് P അല്ലേ? എഴുതാം. ഇനി R വെക്ടർ ബൈ മോഡുലസ് R എന്ന് പറയുന്നതിന് നമ്മൾ R ക്യാപ് എന്ന് പറയുന്നത്. ബിക്കോസ് ഒരു വെക്ടർ എടുക്കുമ്പോൾ അതിനൊരു മാഗ്നിറ്റ്യൂഡ് ഉണ്ടാവും, ഒരു ഡയറക്ഷൻ ഉണ്ടാവും അല്ലേ? ഇതിനെങ്ങനെ എഴുതാം? ഇതിന്റെ മാഗ്നിറ്റ്യൂഡും ഡയറക്ഷനും. സിമിലർലി P വെക്ടർ എന്നുള്ളതിനെ മോഡുലസ് ഓഫ് P വെക്ടർ P ക്യാപ് എന്ന് എഴുതാം. By definition, R by modulus of R is the direction in the R direction. Okay? Direction R, only direction, no magnitude. Magnitude 1. That's unit vector, R cap. Similarly, this is P cap. Is this clear now?
Yes.
Okay. So if you don't know, it's okay to ask. Okay, don't worry.
Okay, thanks.
And let's do one more problem and then stop. Okay. So a simple problem somewhere. All right, let's do another question that was asked for NET June 2013. Okay. The system is governed by the Hamiltonian. H is equal to half Px minus Ay square plus half Py minus Bx square. Okay, where A and B are constants and Px, Py are momenta conjugate to x and y respectively. For what values of A and B will the quantities? For what values of A and B will the quantities Px minus 3y and Py plus 2x be conserved? Okay, so we need to find the value of A and B in such a way that these two quantities are conserved. Right, so let's just take this first. All right, so here I think we'll so we have got a square here, right? We need to take, so we are going to try Poisson bracket. We know that Poisson bracket of this with h is equal to 0 if this is a conserved quantity, right? So we'll demand that, and from that equation we can solve and find A and B. That's how we are going to do it. So we have got a square here. So let's just be a bit careful here. So suppose we have got something like U with F square. All right. The Poisson bracket U with F square. Okay. This you can write it as, sorry, U with FF. Okay. And we already know for this is equal to F into U comma F plus again F into U comma F. Right. We saw this because it's actually U comma F with F, but since it's classical mechanics, we can interchange without any problem. Okay. So this is simply 2f U comma F. Is that fine? Okay. So if you have something like U comma F square or H comma F square, all right, or F square comma H, for example, if you have something like some function square with H, okay, this you can simply write it as 2f F comma H. Okay, we'll use this. Is this all right? Because we have a square here, we can use this directly. Okay, all right.
Okay, sir.
So now we'll check. Let's check for this one first. Okay, what for values of A and B will this be equal to constant? Okay, so if this is equal to constant, then we demand that this with H is equal to 0. All right. only then this will be a constant. So that means that px minus 3y, comma, half px minus ay square plus half py minus bx square is equal to 0. All right. Okay, now, so here, this is a single term. We can use the distributive law. Okay.
Okay.
So we can either write all the steps or just observe and not write the terms that are 0. Right. So shall we try that? So we don't have to write all the terms and then identify it 0 later on. All right. So let's first take px with this term, with this thing. Okay.
Okay.
So we'll combine this px with this thing. We know that this is a function of px and y. So px and px is 0. Px and y is also 0. All right. So there's no term there. Okay. Similarly, we can look at px with this. Px with py is 0, but px with x is 1. So we can write from this term, we can simply write px. You need to take only the second term. Okay, because the other terms are 0. Okay. Is this fine?
Okay, sir.
There's also this term, but that's equal to 0. We have not taken it. All right. Similarly, minus 3y with px is 0 because y with px is 0. Y with y is also 0. Okay. So the only term surviving from this is again 3y comma half py minus bx square. Okay. So this has to be equal to 0. Is this fine? Because there's a y and py there.
Okay.
Okay. Now this, using our rule, this half we can pull outside, and the constants will come out of the Poisson bracket. Okay. Because this involve derivatives. So this is equal to 1 by 2. Okay. We've got px, comma, py minus bx square. All right. So how do we write that? We have got, as we said earlier, u with f square. Right. We said that this is equal to 2. What was the result?
2f.
U comma f. Right.
Okay. Okay.
So this is equal to 2f 1 by 2 py minus bx, right? This is f square, right? And then px with 1 by 2 py minus bx square. Sorry, bx. Is that correct?
Yes.
Okay. 2f multiplied by u with f. Okay.
Okay.
Minus, here similarly you can write 2 to 1 by 2 py minus bx square, right? 2f multiplied by 3y comma 1 by 2 py minus bx. This has to be equal to 0. Is this okay?
Okay, sir.
Okay, so this means that you can simplify this. This is equal to py minus bx multiplied by, what's px with py? That's 0. Px with x is minus 1, right? Px with x with px is 1. Px with x is minus 1. There's a minus sign here. So that becomes plus, and you have got a b and a 2 there. So multiplied by b by 2. Is that correct? I think that's correct. Okay. You got px with py by 2 is 0. Px with b by 2 x is, okay, let's just check this. Px with b by 2 x. Okay. This is simply minus b by 2. But you already have a minus here. So it becomes b by 2. Minus. So we are just using the fundamental Poisson brackets. We are not taking any derivatives. Okay. Minus. This 2 with half is gone. Py minus bx. There's no square there, right? There's no square. Py minus bx multiplied by, we have got 3 by 2. Okay. and y with py, that's only surviving term. There's also y with bx with that, but that's equal to 0. But y with py is 1. Okay, y with py is 1. Is that all right? So this has to be equal to 0. So now this means that py minus bx can be common. Okay, b by 2 minus 3 by 2 is equal to 0. All right. Okay. Fine.
Yes.
Now we are looking for py minus bx equal to 0. That's a solution to this, but we cannot take that because that's trivial. Hamiltonian, we are saying this is a term in the Hamiltonian, right? So taking this 0 is not a good thing. So this term has to be 0. This means that b by 2 minus 3 by 2 equal to 0, or b is equal to 3. All right, that's one result. B equal to 3. Right? And if you look in the option, there's only one answer with b equal to 3. Right? That's a equal to minus 2 and b equal to 3. All right. And in the same way, you can do the other term also. In the same way, we can do the other term also. Just exactly the same. All right. I'll just write it down. All right. Yeah, so b has to be equal to 3. Now we also have, we need to show that py plus 2x. We need to check whether py with py plus 2x is conserved. All right. So you check this. Py plus 2x, comma h, half px minus ay square plus half py minus bx square. Okay, we need to demand that this is equal to 0. But you just follow the steps exactly as before. Okay, we can already take down the non-zero terms. Py with, there's an ay there, so this term should survive. Okay, right? And py with this term is 0. You don't have to write it, right? Because py with py is 0 is py with x is also equal to 0. Right? Now let's check with 2x. Okay, 2x with px that exists. All right. So 2x comma 1 by 2 px minus ay square. Okay, because x with px is 1. You're taking this term and combining with this. And 2x, there's no term, non-zero term from this, non-zero contribution for this. So this has to be equal to 0. All right. Now again, we use the rule that we already found. So if you get complicated expressions like, just try something like, so right, u with f square. Okay, this is always easier to solve. We know this UFF. Okay, and this is equal to UF twice UF multiplied by F. So this is 2F U comma F. Right. So this is equal to 2 1 by 2 Px minus Ay square multiplied by Py with whatever is inside, Py with F. Okay, and Py with F we can already write it. Py with this thing. Okay, so that's there's a 1 by 2. You could always pull out the 1 by 2 in the beginning, all right? But let's do it like this. Okay, I think it's easier to pull the 1 by 2 outside first. All right, so this can be written as, okay, no problem. So this is, let's take this as f square. So it's 2f u comma f, right? So 2 1 by 2 px minus ay 2f and commutator of u with f, okay? And you don't have to write it all down. Py with px is 0, py with ay is minus 1. So this is simply a by 2, okay? Because py with y is minus 1, there's a minus there, that becomes plus, and there's a 2 there, right? You could always pull this 2 half outside and do it. That might be easier. Plus, here, you see that this is equal to, oh, I think I'm making mistakes here. I think I made a mistake because this 2 will not appear there, right? Because this half is not part of the square, right? This half is not part of the square. So I think I made a mistake somewhere. We have to check. But we got the answer correct. Luckily, I'll just be more careful, right? because this half is not part of f square, right? You please correct the previous step. The answer is correct, right? Because whether it's b by 2 minus 3 by 2 equal to 0 or b minus 3 equal to 0, you get b equal to 2. But this 2 won't be there. I'll show you why. You have to first pull this half outside. Okay, you have to write this step once more. Px minus ay square. Only now it's in this form. Am I right? Am I right? And this 2 1 by this 2 into 1 by 2 is 1. So this is simply x comma px minus ay square. Okay. So I made a mistake earlier because this half is not part of the square over there. You cannot use the result. All right. Now you can use. This relation is also there. I'll show you. Okay. This relation is also there. Okay. If you have u with cf, okay, this is equal to c multiplied by u comma f. Okay, that's another property. Okay. You can check it easily. It's easy to check. Okay. All right. Because the derivatives are little. Derivative term is c value. Okay. You can simply pull it out. Okay. So you can use that. So all constants can be pulled out. Okay? I'm sorry about this. You really have to correct it. All right. The steps. Okay. Mistake മനസ്സിലായോ?
1 by 2
1 by 2 ആദ്യം പുറത്തെടുക്കണമായിരുന്നു കാരണം ഈ relation the 1 by 2 it's not part of the square, all right? So it's better to take this constant outside. Okay, so you will have b minus 3 equal to 0. I'm sorry about this, but I hope it's clear. 1 by 2 you pull outside, so this is okay. What was our result? Py with a square, so this is equal to 1 by 2 px minus ay. Okay, 1 by 2 2f multiplied by u with f. What's py with? That's equal to py with ay, py with minus ay, that's equal to simply a. Okay, plus from here you have in the same way px minus ay. We have twice there, right? 2f into u comma f, and x with px is simply 1. That's equal to 0. Okay. All right, so which means that px minus ay can be pulled outside, common from here. You have got a and plus 2, am I right? And you don't want this px minus ay equal to 0, that would make the Hamiltonian different. So a has to be equal to minus 2. Okay, so the answer we need is a equal to minus 2 and b equal to 3. All right, we were lucky in the first part to get b equal to 3 in the correct way, even though we messed up with the factor of half. Okay, is this fine? You can do such problems. You just need a little bit practice. All right, if some squares come, you just check this u comma f square and use the properties, and you see that this is equal to 2f into u comma f. All right, you can also look for a relation for u of f raised to n. Okay, but it doesn't matter. You can just instead of remembering the relation for this, you can just do it every time and find it. Okay, just do it in the margin. In 2 steps you'll get a result, and then you can directly apply it to this. Okay, only thing you have to be careful about, always pull out all the constants from the Poisson bracket. Okay, so this is how we do it.
uf raised to n എന്ന് പറഞ്ഞാൽ nf into uf എന്ന് എഴുതിയാൽ മതിയല്ലോ സാറേ? എങ്ങനെ? u, f raised to n ആണെങ്കിൽ f into Poisson bracket of uf എന്ന് എഴുതിയാൽ മതിയല്ലോ?
എനിക്ക് തോന്നുന്നത്, I think you have to check it. I think this will be nf multiplied by uf raised to n minus 1. Okay, I think that's the correct thing, but you have to check.
Okay.
How do you check? You check for u comma f square, you know. You check also for u comma f cube. Okay, use mathematical induction.
Okay.
Okay, and I think this is what you will get. Okay. But you have to be careful. Right? So if it is this n is equal to 2, then it's 2f u raised u comma f, right?
Okay.
So then if it is cube or 4, then you will have to use this result a few number of times. Right? If it's a cube here, you will have an f square here, then you have to again use that relation. But I don't think they will ask such problems. And this problem, it's not so complicated, all right? If you are really familiar with the steps, you will get a result very quickly. Now you can also try with taking the derivative. That might be easier here, right? You can also try by finding the derivative, okay? So that you can do as a homework. Check the Poisson bracket using definition. Okay, you can do that. All right. Do you have any doubts, or we'll wind up now?
Okay, sir.
Okay, thank you.
Thanks.
Okay, മനസ്സിലാവുന്നില്ലേ?
മനസ്സിലാവുന്നുണ്ട് സാറേ. സാറേ ഇനി നെറ്റിന്റെ വിളിച്ചില്ലല്ലോ സാറേ ഈ പ്രാവശ്യം?
ഇതുവരെ വിളിച്ചിട്ടില്ലേ?